All right, so welcome again, guys. We're gonna do a little recap from last week, where we started to do a question on moments. Moments is one of the topics that CXC has sent. So what we try to do is to cover as many questions as possible for each topic. So last week we had started to look at a question from the moments section of the syllabus. And this question is actually from the recent paper of January 2021. First part says, state the principle of moments, and that's 3 marks. We have the answers prepared. So for this question, you just need to state the principle of moments, which is a recall question. So all you need to do is to remember what the principle of moments state, and you will get your 3 marks. All right, so the principle of moments is that in order for a body to be in equilibrium, and equilibrium means that it is balanced and not falling over, the sum of the clockwise moments about a point must be equal to the sum of the anticlockwise moments. So I think the word sum is missing from this, but it should be the sum of the anticlockwise moments here about that same point. All right, part B says, state another condition that is necessary for a body to be in equilibrium. And this is 1 mark. So the other condition is that the sum of the forces in any direction or in a particular direction must be equal to the sum of the forces in the opposite direction. So if you consider some forces that are acting upwards and you add them, then when you add the ones that are acting downwards, the 2 answers should be the same. Part C says, state the formula for the moment of a force, providing the meaning of each variable and its SI unit. So from the definition of moments, if you know the definition, moments is defined as the product of the force and the perpendicular distance of its line of action from the pivot. So it's essentially force times distance. And for the formula, we have T for moments and F for force, of course, and D for distance. Please note the case that is used, uppercase letter T for moment and uppercase F for force. Distance is lowercase d. All right, so this is the formula, and then we have the meaning of each letter, each symbol, SI unit in brackets. All right. Okay, so the SI unit is Newton meter. All right. Next part is so we have a diagram here with a girl standing on a uniform plank, which is 3 meters in length, and the girl is 270 newtons in weight. And we are to or we are given the scale readings. These scale readings are in newtons, so they are measuring the force. And see, the first part of the question says, on figure 3, we are to draw and label all the forces acting on the plank, and that's 2 marks. So apparently for this question now, it's not 1 mark for each labeling, but maybe quarter mark or so. Okay, just a correction. The 270 is the weight of the plank and not the weight of the girl. All right, so you may get maybe a quarter mark for each correct answer. Here, not 1 mark because you have several forces, but only 2 marks. So the first force we can label is the reaction force at the support here from this first scale P. And this reaction force, we can call it R1. We have a second reaction force, sorry for the displaced labelings. So maybe the size of the diagram was changed after, but this should be right here. So this one is R2, that's the reaction on the support at Q, scale at Q. Then we have the weight of the plank, that's 270 newtons. And finally, we have the weight of the girl, which is unknown at the moment. All right, so this, so we have 4 labelings for 2 marks. So most likely it's quarter mark for each. But if you only get 1, they won't give you a quarter mark. All right, or they won't give you a half mark for 2. So you must get at least 3 of them correct, because there is no quarter or half mark to be given. Next part of the question, calculate the girl's weight. And we have a completed diagram just to remind us. And what we do is to look at what R1 and R2 are equal to first, because from Newton's third law, we know that whatever force is registered on the scale, that same force will be acting upwards at the where the plank is being supported, right? So the upward reaction forces are 354 newtons and 417 newtons respectively. And if we, well, the first thing you normally do in questions like these is to find the sum of the forces in one direction, the ones that you know, and then equate it to the sum of the forces in the opposite direction, because this will involve one or more forces. Well, usually one force that you don't know the value of. This is the one that you want to find. So if we know R1 and R2, then we know that the total of R1 and R2 should be equal to the total of 270 and W. So then we substitute for W in the equation and we find it to be 501 newtons. Question E, by taking moments about Q, calculate the girl's distance from the scale at Q. So taking moments about Q means that you're going to take all your distances, all your distance measurements from Q. All right. So we also will consider the turning to be taking place, the turning effect from Q and not anywhere else. So the clockwise moment would be, so you look at which force will cause the Planck to turn clockwise, and that would be R1. If R1 was acting, and if R1 was acting from the pivot here, then it would cause the Planck to turn clockwise. All right, so it'll go over in that direction. So 354 times 2, it is 2 meters away from Q. All right, based on this measurement here. So 354 times 2 is equal to the sum of the anticlockwise now. And for the anticlockwise, we would have 270 times 1, because the 270 here would be at the center of the Planck. All right. So 270 times 1 plus the weight of the girl multiplied by her distance. All right. So we substitute and transpose in the equation. You could have written the equation for the sum of the clockwise and the sum of the anticlockwise, and you substitute. All right. So you're going to make D the subject of the formula, and D would be equal to 207 Newton meters divided by 501 newtons. Newtons cancel, leaving your answer in meters. All right. In case you didn't recall, or you don't recall what the answer, the unit should be, then you know that you can figure it out from the calculation. All right, so we are going to start session 3 proper with these topics. We're going to look at alternating current, resistance, magnetic forces, electromagnetic force, and motors. Of course, we'll be looking at past paper questions that come from these topics. All right, so basically what we'll be doing is that I will be going through the content to summarize the concepts for each topic, and the Miss Rose will go through the questions. All right, alternating current. All right, so you can use this table for your own purpose, but I'll be just going through some of these points. In the left-hand column, we have what you should know. So these are the concepts, maybe definitions and so on. And then in the right column, we have what you should be able to do. And this is coming from the syllabus, right? So what you should know for alternating current, first thing, you have to know what is direct current as well, right? So direct current Now, this is where the current direction, or the direction in which the charges flow, remains the same. There is no change in the direction. Whereas in alternating current, or AC, the direction in which the charges flow reverses regularly in a repeated fashion. Now, the rate at which the direction of flow changes is known as the frequency of the AC. So the AC current has a frequency. You don't have any frequency in the direct current. All right. And that's frequency represented by F. Now, the time it takes to complete one cycle is called a period, and that's designated T. Similarly to in a wave, all right, wave motion and a pendulum. So F and T are reciprocals of each other. So it follows the same concept as in waves and the simple pendulum. All right. So frequency, number of cycles per second, period is the time taken for one complete cycle. All right. So for it to go one direction, come back and go in the opposite direction and then start over, that time is the period. And as we said, the frequency and the period are reciprocals. So to find the frequency, you need to know the period, or to find the period, you need to know the frequency. But once you know one, all you need to do is to divide one by that you know to find the other. All right. So if you know the frequency, you divide one by the frequency to get the period. If you know the period, you divide one by the period to get the frequency. Now, many persons may not have heard of this device, but you should be aware. You don't need to know any technicalities, but it is used to show, it can be used to show the waveform of an electrical or an electronic system, all right, allowing us to measure and analyze the features of whether it's AC or DC. And it may look like this. But you just need to know that it exists, not to know the workings of it or so. So you can see the waveform on the CRO, cathode ray oscilloscope. All right. So this is what is used to show the waveform. If we want to know if a system is AC or DC, we could use this device. All right, so we have an illustration of alternating current and direct current. So the first graphic is showing alternating current, and the red what you call those dots, they are the electrons, and as you see, they keep on changing direction. So at one point they are going clockwise, at another time they are going anti-clockwise. All right. While on the right, this graphic is showing direct current. The dots are always going in the same direction when the switch is closed. All right. So there is no change in the direction. Electrons move anti-clockwise in this case at all times. Now, another or a more representative way in which we differentiate between AC and DC is to use graphs of current, either current or voltage against time. And in this diagram, it's current against time. And we see one type of, this is representing one type of DC, and this is representing another type of DC. All right. In this one, the DC is constant over time. The value doesn't change. The direction also doesn't change. So what we consider on a graph like this is the positive and negative halves of the graph. Positive is one direction, and the negative is the opposite direction. All right. So this is how you should understand the graph, and not as in negative current and positive current, but direction. All right. In this one, the DC is not steady. The current or voltage is not steady. It is pulsating. All right. So it goes up to a maximum, come down to zero, and then follow that pattern again. But it doesn't go in the opposite direction. It is still in the same direction, just that its value is changing. All right. So its value is getting higher and lower, but the direction is not changing because we don't find the graph going in the negative region, which means the opposite direction to that of the positive region. All right, so both of these would be direct current and alternating current. We have the first one here, which is a sinusoidal pattern. So it goes from zero to a maximum in one direction. Its value will decrease to zero, and then it goes in the opposite direction and go to a maximum value in that direction and return to zero. That's one cycle. If we start here, from time from here to here would be the periodic time. All right. So this is how the alternating current behaves. Its value increases and decreases, but it also changes direction with time. We can also have a square wave pattern where the value keeps constant for a while, drops to zero, then it flows in the opposite direction, goes to a maximum, stays at a maximum for a short time, then fall to zero again. All right. So the time here, if we consider from here, then going back up here, that's one period. So this would be approximately 30 milliseconds for the period. So this is AC. All right, so we have a question which is based on AC, and Ms. Rose will take over there.
All right, good afternoon, everyone. This question is from the January 2020 paper, the recent paper from last year. And we are looking at question 5B and C. So the first part says that with the aid of a circuit diagram, you should describe how an alternating current, which is AC, can be half-wave rectified to produce a direct current or DC across a resistor. And that's 5 marks. Now, this question is basically talking about an aspect of electronics where we look at using a semiconductor diode to change or to basically cut away one half of an alternating current cycle. So what we have to do is, in setting up the circuit, ensure that we have an alternating current supply for the input, and that is going to be connected directly to a semiconductor diode, and the diode is then going to be connected to a load resistor. Now, the most important function of the semiconductor diode is that when it is in a particular direction, which we call forward bias, it allows current to flow, which is like it allows current to flow in a regular manner. However, if the diode is switched around, it is in reverse bias, and in that case, it acts like a switch in the off position. So what we have here is that with the alternating current supply during the positive half cycle, the diode is in forward bias, so current is allowed to pass through the diode and through the resistor. So you would get the positive cycle or the positive half of the cycle at the output. However, during the negative half cycle, the diode appears to be in reverse bias. So the current that flows in the negative half cycle is not going to pass through the diode. So as a result, there is no current in the circuit, and so there is no voltage drop across the resistor. So we only end up with the half wave, the positive half cycles of the alternating current. Now we get direct current. However, it's not going to be a steady direct current, but it will be pulsating. And the next part of the question actually explores how the waveform will look. Right. So the next part says that we are to sketch the voltage time graph to show the expected output across the load according to the first part. Now, as we mentioned, the negative half cycles will be cut off. So it means that there is not going to be any part of the wave that shows below zero. So that direction will be cut off, and only the positive half cycles will be shown. So you will end up with a pulsating direct current. So the value is going to increase from zero, reach a maximum, decrease again, and then it will remain at zero for a time before the value increases again and decreases. So notice that there is no negative half cycle because the diode would have cut off that section of the current. So we only have the positive half cycles. And once the current flows in one direction, then it is classified as direct current. All right, so part C says to draw a voltage time graph showing an AC source with a frequency of 5 hertz and a peak voltage of 12 volts. Right? So the paper was provided and it was already labeled and everything. Now remember, it's an alternating current source. So it means that the peak voltage, which is 12 volts, it should achieve the peak voltage in both the positive and negative directions. Now, before we can actually draw the graph, we need to make sure that we take into consideration how long it will take for the current to achieve one full cycle, meaning one positive cycle, positive half cycle, and a negative half cycle. So we can refer to our equation that says the period is equal to 1 divided by the frequency. Frequency is 5 hertz, so we divide 1 by 5 and we get 0.2. So if one full cycle takes 0.2 seconds to complete, then it means that half of the cycle would take 0.1 second to complete. So we end up with the positive half cycle, and you realize it reaches the maximum of 12 volts, and then back to 0 in 0.1 seconds. And then the negative half cycle would take place in the same amount of time. So it will reach a maximum of 12 volts in the opposite direction, and then back to 0 for 0.2 seconds. So when we look at the graph, you have one half cycle taking place and another half cycle. The total time for that to complete is 0.2 seconds. And then we could just continue that path to fill up the rest of the page or the rest of the graph paper. Right? So it's important that the peak voltage is achieved in both the positive and negative directions, and each full cycle takes 0.2 seconds to complete. So the second cycle would take another 0.2 seconds, which means the second cycle would finish at 0.4 seconds, and so on. All right. Now, this is another question taken from the May-June 2011 paper, and we are doing question 3B. Now, there's a table that will be presented, and there are some waveforms for A, B, and C, and we need to determine the type of current. Now, the key thing to remember is that once it is direct current, there is flow in only one direction. So it's either gonna be everything in the positive direction or everything in the negative direction. However, with alternating current, you have the current varying in both directions. So we can look at A, notice that as the graph proceeds or as the wave form progresses, it reaches a maximum and then it goes to 0, but it does not change direction. It stays at 0 for a while and then it goes to a maximum again. So because the current is in one direction, we can classify this as direct current, right? And this would be similar to the half wave rectified AC current that we looked at a while ago. So that's direct current for A. For B, this one is a little bit more straightforward. The current doesn't change direction and it stays at the same value throughout. So this is also direct current, and it would be steady direct current. Now for C, notice that the current varies between the positive and negative directions. So we can determine or classify this as alternating current. This is an AC sine wave. Right. So for waveform C, we're asked to determine the period and the frequency. Now remember that the period is the time that it takes for the wave to complete a full oscillation. So both positive and negative half cycles must be completed in order for it to have completed a full cycle. So notice that half of the wave, the positive half cycle, takes place in 0.1 second, and then another 0.1 seconds for the negative half cycle. So from 0 seconds to 0.2 seconds, that would take in a full wave. So we can see then that the period would be 0.2 seconds. All right, so that's 0.2 seconds for the period. And now that we know the period, we can recall that the period and the frequency are reciprocals of each other. So we can apply the formula that if T is equal to 1 divided by F, then F is equal to 1 divided by T. So we divide 1 by the period of 0.2 seconds, and that gives us a frequency of 5 Hertz. Right, so we're going to be moving on to our next topic. Mr. Campbell will take over again from here.
All right, so we're looking at resistance. Now, first thing is that resistance as a concept is provided by Ohm's law. And we can define resistance as the opposition to the flow of current or opposition to the flow of electric charges. Either one will do. It is measured in ohms, of course, from George Ohm, who investigated the concept. And we define the ohm, meaning 1 ohm is the resistance of a conductor through which a current of 1 ampere flows when a potential difference of 1 volt is applied across its ends. So this is the definition. This is how we get 1 ohm. So every multiple of this, all right? Every multiple of the ohm comes from this definition. All right, so resistance of a wire, for example, will depend on 2 main factors if the temperature is constant: the length of the wire and the cross-sectional area. Or we could say in layman terms, the thickness of the wire. Now, the longer the wire, the more resistance it will have. All right. And the thicker the wire, the less resistance it will have. Okay. So if you have a long wire, it should be thick enough to balance out the high resistance coming from the length. All right. But if you have a long wire and it is thin, it will have a very high resistance. Okay. Now, ammeters and voltmeters are going to be measuring current and voltage respectively. However, the resistance of these devices are important because they can affect the reading that you get. So in making these devices, they have to consider the resistance that they have, because once you put something in a circuit, once you put a component in a circuit, its resistance has to be considered. Now, because, well, ammeters are placed in series, so we know this first. So when we measure the current through, we place the ammeter in series with the component or with that part of the circuit, while the voltmeter would be placed in parallel, right? So the first thing you are to appreciate is their placement, all right? How they are placed in the circuit. Because once you realize that, then you should be able to explain why the ammeter should have a very low resistance, all right? So the ammeter should have a very low resistance so that it does not add to the total resistance in the circuit. But you have to remember that in series, the resistance add up, all right? If you have 2 components in series, the total resistance or the effective resistance in the circuit will be the total of the 2 components. So by putting in the ammeter in series, if the ammeter has a relatively high resistance, then it will add to the total resistance, and that will cause the ammeter to give an incorrect reading. So basically, the ammeter should measure the current but not affect the current. Voltmeter, on the other hand, should have a very high resistance so that negligible current flows through it. Right? Negligible means that we can ignore it. Some amount of current must flow through it for it to work. However, it should not be, the current flowing through it should not be of any significance. So if you get an ammeter with a high, not a high resistance, then it is going to cause the total current in the circuit to change, and that will affect the reading that it gives. All right. All right. So from the syllabus, you're to be able to explain why the ammeter should have a low resistance, very low, and why the voltmeter should have a very high resistance. All right. I should be able to demonstrate this concept, this last one. So I'm going to try to demonstrate that. So I'm going to pause for a while. Okay, so here we have a circuit. We have a parallel circuit to simulate the voltmeter with the high resistance. All right, what I should have done is I'm going to put the low resistance resistor inside the circuit just to show. All right, but in the first place, what I'm going to do is to show you what current is flowing. We have 0.9 amperes flowing in this circuit. All right. But if we add a resistor in parallel, remember in parallel, the resistance of the circuit will decrease. So you're going to get more current here. All right. This is just a series circuit. No current is flowing through here because we have a disconnection here. We don't have a connection here. But if the connection is made, you're going to find that the current here is going to increase. So we are going to use this as a voltmeter with not a high resistance, or with a relatively low resistance. So watch what will happen. By connecting this one, or just imagine this to be a voltmeter. Remember, the voltmeter is connected in parallel. So suppose this was a voltmeter, right, this here, and it's connected in parallel. We want to measure the voltage across here. All right. What will happen? We're going to get some current flowing through the voltmeter here, and then the total current in the circuit will increase. So what this means is that the voltmeter here would not give you the correct reading of the voltage that should be here, because it is taking some of the current. All right. However, if we place a high resistance voltmeter, so what I'm going to do is to replace this resistor with one that is of a very high resistance. And if you look, this one is 10,000 ohms, very high resistance. When we close the switch, basically no current flows through it, and all the current still flows through part, the resistor here. All right, so we still get the current that should flow. And if this was a voltmeter, then it would give you the correct reading. All right, so that's why the voltmeter should have a very high resistance. All right. All right, continuing with what you should know for resistance. If we have components in series, the total resistance is the sum of the individual resistances. In fact, we use the word total here, all right, to mean, the algebraic or arithmetic total or sum. So you just add them. If you have two resistors in series, you add their values to get the total for the circuit. However, if you have two in parallel, it is not as simple as adding them. We have to find the reciprocal of each one and add those reciprocals. And that sum will give you the reciprocal of the effective resistance. All right, so basically you'd have to do a much more complex calculation if you have resistors in parallel. All right. All right, so you should be able to solve problems involving series and parallel resistance, and solve problems involving series, parallel, and series parallel circuits. So you may get a circuit with only series or only parallel or a combination of the two. All right, so when you look at the question, you will, if you don't know already, then you will see how questions are solved with resistors in series and parallel and so on. All right, so we have a question from the May-June 2015 paper, question 3. Ms. Rose will take over again.
All right. So for this question, the first thing that we are required to do is to explain what is meant by the term electrical resistance, and that's for 1 mark. So it's just to state the definition for electrical resistance, which is basically the opposition to the flow of current. Right, so that's 1 mark. And then the next section is based on electrical meters, which Mr. Campbell just took us through in great detail. So we need to complete the table to provide information regarding different types of electrical meters, the ammeter and the voltmeter. So there's a column for filling in how it is that these devices should be connected, whether in series or parallel. There is one for whether the resistance should be high or low. And the final column is for us to state the reason for the size of the resistance. So for the ammeter, which we use to measure current, as was described earlier, the ammeter needs to be connected in series with the components, and it needs to have a very low resistance so that it does not disrupt the current flow through the rest of the circuit. All right. So as we said, it needs to have very low resistance so it doesn't add to the resistance in the circuit and basically disrupt the true current reading. Now the voltmeter should be the opposite. So if the ammeter needs to be connected in series, the voltmeter has to be connected in parallel, and it needs to have a very high resistance. All right. So it needs to have a very high resistance so that it does not take away from the amount of current that is flowing through the entire circuit, right? So if we have a reduction in the amount of current flowing through the circuit because of the presence of the voltmeter, then it is going to give an incorrect reading for voltage. All right. Now, this question requires some circuit analysis. So the figure basically has a 12-volt battery, and there are 3 ammeters that are connected. Now it's important for us to, even before we start looking at solving the problems or figuring out what the different readings need to be, we need to look at the circuit carefully and identify whether the components are connected in series or in parallel. So for argument's sake, let us say that the 2 ohm resistor, we can call that resistor 1 or R1, this 2 ohm resistor here, the one, the top, we can call that one R2, and then the 4 ohm resistor, we can call that R3. Now notice that if we look at the circuit, the 2 ohm R2 and R3, let's call it that, both of them are connected in series because you realize that there is just one path through which the current can flow through each of them. That's for R2 and R3. However, for R1 is in a branch by itself. So we can say then, if we're describing the circuit, that R1 is in parallel with R2 and R3, while R2 and R3 are in series with each other. All right. So in order to determine the reading on A1 is basically going to give us the current, the total current that flows through the entire circuit before it has to split to go through R1 and then R2 and R3. So we first have to find the combined resistance in the circuit. Now remember we said that R2 and R3 are connected in series. So if we need to find the total resistance for those 2 resistors, we just add the individual resistances. However, R2 and R3 are connected in parallel with R1. So for finding the combined resistance for a parallel circuit, we have to use the relationship that says that 1 over the total or combined resistance is equal to 1 over the sum of each of the different resistors. So 1 over R1 plus 1 over the sum of R2 plus R3, because R2 and R3 are in series. When we get the combined resistance there, those 2 resistors would be in parallel with R1. So that's why we have to state the equation like that. Of course, you could also do it separately. You could find the combined resistance in series and then apply the formula to find the combined resistance for the entire circuit. All right. So we just substitute R1 is 2 ohms, so is R2, and R3 is 4 ohms. So when we go through and we add everything, we end up with a total reading of 1.5 ohms. So the entire circuit has an overall resistance of 1.5 ohms. Right. So we're now going to find the current by applying Ohm's law. Ohm's law, in mathematical terms, V is equal to I times R. So if we transpose and make I the subject, I is equal to V divided by R. So we want to find the total current. So we use the total voltage, which is 12 volts, and we divide it by the total resistance, which we just found to be 1.5 ohms. So 12 divided by 1.5 is equal to 8, and our current is 8 amperes. Mhm. Any questions so far, by the way? All right. So we'll move on to part B. This question is from the 2015 paper, so it's a separate paper. Oh, sorry, it's the same question. So we just found the total current, and we need to find the current that is flowing through A2, which is the second ammeter. And that is basically the current that is flowing through R1 only, right? Remember, R1 is the resistor that's on the side there that's connected in parallel with the other, right? So remember that we can use Ohm's law as we do for most of the circuit, most if not all circuit analysis questions, we have to apply Ohm's law. Now remember that R1, sorry, is connected in parallel with the other components. And in a parallel circuit, the voltage in each branch is the same as the total voltage or the EMF of the battery, right? So we can simply apply Ohm's law and divide the voltage, which is 12 volts, by the resistance of 2 ohms, and that will give us 6 amperes. So of the 8 ampere that flows in the entire circuit, R1 receives 6 amperes, and then R2 and R3 would both receive 2 amperes. So the same 2 amperes of current would flow through R2 and R3, and 6 amperes would go to R1. So we have another question from the recent paper for the 2010-2011 academic year. And we have some circuit symbols and the names of the various components. So we are asked to complete the table. So for the first one, notice we have a, a long stroke and a short stroke representing a positive terminal and a negative terminal respectively. It's one single positive and one single negative, and that represents a cell. Now, if you have more than one positive and negative, or two cells or more connected together, then we would call that a battery. Now we are required to draw the circuit symbol for the variable resistor, and there are two symbols that are used. We can draw a regular resistor symbol and place an arrow through it, or we can use the second symbol there with the arrow on top. Okay. The third symbol, this is the symbol for the filament lamp. And fourthly, we have an alternating current supply. And second to last, we're required to produce the diagram for the semiconductor diode. We looked at it a little earlier. So you would just draw the triangle, ensure that you place the vertical line at the apex of the triangle, and that's our diode symbol. Now, finally, we have the circuit symbol. There are two symbols, and we use them to represent the fuse. All right. So part B, we have some more circuit analysis to do again. So this circuit diagram, there is there are three resistors present, But with the current arrangement, notice that the switch S is open. So R3 currently is not receiving any current. So if you look at it from that angle or that standpoint, you could basically ignore R3 for now and note that R1 and R2 would be connected in series with each other. All right. So the description says that R1 is 4 ohms, R3 is 8 ohms, and the supply is 24 volts. When the switch is open, the total current is 2 amperes. So we'll have some questions to answer based on that. Right. So first, we need to state the formula that relates the voltage to the current and the resistance. And that's the mathematical statement of Ohm's law, which is V equals I times R. So voltage is equal to current times resistance. Now we need to calculate the value of R2. Right now, remember that we're ignoring R3 for now because the switch is open. All right. So if we know that R1 and R2 are connected in series, then it means that the current that R1 and R2 both receive is the same 2 ampere. So we can therefore find the total or the combined resistance by applying Ohm's law. All right. So resistance is equal to voltage divided by current. So we can find the total resistance by dividing the 24 volts by 2 amperes, and that gives us 12 ohms. Now, because the 12 ohms is the combined resistance, and we know the value of R1, we can find R2 by subtracting the 4 ohms from the 12 ohms, and that would give us 8 ohms for the resistance of R2. We are now required to work out the reading on the voltmeter. Now, in a series circuit, the voltage is shared between or among the components. So of the 24 volts, R1 is going to get some and R2 will get some. So based on the resistance of R2, we can use the resistance and the current to calculate the voltage. So V is equal to I times R. The current flowing, as we know, is 2 amperes, and the resistance is 8 ohms for R2. So realize R2 is, the voltmeter, sorry, is connected across R2. So we'd use the resistance of R2. 2 amperes times 8 ohms is equal to 16 volts. So of the 24 volts, R2 will receive 16 volts. Now, finally, we are asked to calculate the new reading on the ammeter if the switch is closed. So now, basically, R3 is operational. So we are now required to calculate the new current that flows through the entire circuit. Now, once the switch is closed, then we would have to remember that R2 and R3 are going to be connected in parallel with each other and in series with R1. All right. So that's the first thing that we need to note. So as a result, we can now use Ohm's law again. So we'll use the resistance formula to calculate the resistance in parallel. So R2 and R3, effectively, we'll have a resistance. We can call that RP for our resistance in parallel. And we can use the rule that says for two resistors that are connected in parallel, we can find the product of the two resistances and divide it by the sum of the two resistances. So both R2 and R3 have a resistance of 8 ohms. So we would multiply 8 times 8 and divide that by 8 plus 8. So we would get 64 divided by 16, which is 4 ohms. All right. You could use the other expression where we would say 1 over RT is equal to 1 over R2 plus 1 over R3. But we'd have to remember that when we work out our answer, we need to find the reciprocal. All right. So it's being written on the board. So we can use that relationship as well. Okay. So this is how we can find the effective resistance in a parallel arrangement. However, if there are two resistors or two components in parallel, you have the option of using the product over the sum, or the product divided by the sum. So now that we have the effective resistance of the parallel section, which is R2 and R3 together, we can now calculate the total current. Remember that R2 and R3 together, you could replace them with a single 4 ohm resistor, which would be in series with R1. So we can use the total resistance in the entire circuit would be 4 ohms, which is the resistance of R1, plus the combined parallel resistance, which is 4 ohms as well. So we would have a total resistance of 8 ohms. So we can then use current is equal to voltage divided by resistance. The total voltage is 24 volts once again, and we divide by the sum of 4 plus 4, which is 8. 24 divided by 8 is 3 amperes. All right, so remember, once we add components in parallel, the amount of current increases overall. All right, and that's it. So we will be moving on to our next topic, which is magnetic forces.
Okay, so for magnetic forces, we're going to look at what you need to know. So the magnetic force is that which is exerted on a ferromagnetic object or objects which are within the magnetic field. Now, this force is strongest at the poles of a magnet, and it decreases significantly the farther from the poles the object is. All right, so strongest force for a magnet or from a magnet is at the poles, N pole and S pole. Now, the force between like poles is one of repulsion. So there's a repulsive force between like poles, and we can, while the force between unlike poles is one of attraction. So we have an attractive force between unlike poles. We can state this in another way as the what we would call the law of magnetism, which says that like poles repel and unlike poles attract. All right, from the syllabus, it says you are to be able to investigate the forces between magnetic poles. And this is normally when they say investigate, it means maybe by in a practical way, but we should be able to also use a thought experiment to figure it out. Now, the other things that we should do now is, or what you should know is, a magnet exerts a net force of attraction on unmagnetized object by a process called magnetic induction, right? So when a magnet attracts like a nail, the process by which it does so is called magnetic induction. Now, the magnetic field is the region around a magnet or moving electric charges in which the magnetic force is exerted. All right, so a magnetic field exists around a magnet, but it also exists anywhere you have moving electric charges. A magnetic field line indicates the direction of the magnetic force acting on an end pole. So whenever you're drawing the magnetic field lines, or whenever you see them drawn, you are to always note that the arrows should point from N to S. All right, always from N to S. All right, so we have an illustration of magnetic forces. All right, if two S poles are facing each other or aligned with each other, we get repulsion. But if an N and an S are aligned, we get attraction. N and N, repulsion. S and N, attraction. So whether it is N then S or S then N, there will be attraction. All right, so the magnetic field for a bar magnet is represented like this. Notice the arrows always point away from N and towards the S. All right. If we have an N and an S aligned, we're going to have a different pattern between them. So we'll have the lines actually, some of the lines actually stretching from the N to the S. All right. So you have to know these, and not to say to really swat them off, but to understand how they are obtained. And one way in which you can understand it is to imagine putting an end pole, if it were possible. Imagine placing an end pole anywhere around the region where you want to find the magnetic field, and just imagine where it will go. All right, if you place an end pole. So just do a thought experiment. Put an end pole here. Where would it go? It would be repelled, of course, from this end pole, but it will also face the attraction from this S pole. And so the line will curve around from the N to the S. While if it was here, then it would go straight across. All right. Likewise, if you want to find the field for two end poles aligned, you imagine placing an end pole anywhere here. Of course, if you place an end pole here, it will be repelled by this end pole, but it will not get too near to this other end pole, and so it will be diverted upwards. All right, so once you figure out on one side, it's mirror image on the other side. In the middle, we'll have no lines because of the fact that anything placed here will be experiencing equal but opposite forces on itself, sorry. All right, so if you put an end pole here, it will be pushed away by this one, to the right and then pushed by this one to the left, and so they cancel out each other. So you'll have no lines in the middle. All right, this shows a quantitative analysis, but you should understand only from a qualitative perspective how does the value of the force change as the distance between the magnets get larger. All right. In this case, there is an attractive force, so between an N pole and an S pole. And what you see is that when they are not separated, so the distance is 0, then you have the strongest attraction, which is about 20 newtons. But as the separation increases, the value of the force decreases significantly. So we get a line curving downwards. All right. So this tells us that the force is inversely proportional to the distance between the magnets. All right. You need to know this from a qualitative perspective. All right. So F is proportional to 1 over D, which is saying it is inversely proportional. All right. Because 1 over D is the inverse of D. All right, we have a question here from May, June 2005. So 16 years ago. Miss Rose will do this one.
All right. So this question basically tests your knowledge of the interaction of magnetic fields. First, we are asked to explain what is meant by the term magnetic field. And as was said earlier, it basically is just the region that surrounds a magnet or moving electric charges in which the magnetic force is exerted. Okay. For part B, we are asked to sketch the field pattern for two arrangements of bar magnets that are placed close to each other. So for the first one, notice we have two north poles being interacting with each other. And as we know, like poles will repel each other. And of course, before we draw, we should always remember that we draw our field lines going away from the North Pole and towards the South Pole. So you would end up with an arrangement like this, where in the middle, as was discussed earlier, there would be no force because of the presence of the two North Poles that would repel each other. And you would have attraction between the North and South Pole of the respective magnets to their relative North and South poles, but not to each other. All right. So the field lines would look that way. For the second arrangement, there are North and South Pole facing each other, and like poles will attract. And once again, we should remember that the lines from the North Pole should be oriented towards the south. So you will have attraction between each North Pole to the South Pole. All right, so you'll have attraction in the middle there, and you also have the attraction between the North Pole and the South Pole of the respective magnets. All right, so it's important for us to make sure that we have the arrows in the right direction. And in the middle, ensure that you have the field lines being strongest there or closest together, indicating that the magnetic force is strongest at this point. And that's why we have the attractive force. Right, so I think that's it. So we are going to be moving on to electromagnetism now, and we'll discuss the concept of electromagnetic force.
Okay, so for the electromagnetic force, now this is a force that is created when a current carrying conductor is placed in a magnetic field. All right, so there will be a force acting on a current carrying conductor if it is placed in a magnetic field, meaning close to a magnet or between the poles of two magnets. This force is what we call the electromagnetic force. Now, the direction of this force on the conductor is dependent on the direction of the current and the direction of the magnetic field, in which all three are at right angles to each other. So as long as the conductor is placed perpendicular to the magnetic field, then we will have an electromagnetic force acting on it, which is in a perpendicular direction to the current and the magnetic field. All right, so all three directions will be perpendicular to each other. We can predict this direction, meaning the direction of the force on the conductor, by applying Fleming's left-hand rule. So you must know Fleming's left-hand rule, and it can be easily done using your left hand, of course, but you need to know what each finger represents when using the rule. Now, this image will show you Fleming's left-hand rule being applied, or how it is to be applied. So we have, or you should place or position your left hand like this, so that your thumb, your first finger, and second finger are at right angles to each other. Right. Now, what you do next is to align your first finger in the direction of the magnetic field and your second finger in the direction of the current, and your thumb will point automatically in the direction of the force or the motion. All right. Any questions? Any concerns here? All right, so in order to remember, thumb, M in thumb is for motion. The F in the first finger is for field. So this gives the direction of the field. The thumb gives the direction of the motion, or the direction of the force, because the conductor will move in the direction as the same direction in which the force is acting. All right. And the C in second is for current. That's the conventional current in the wire. All right. So you need to remember conventional current, or what is meant by conventional current. When we get there, we'll just illustrate or remind persons what we mean by that. So remember, thumb will give you the direction of the force or the motion of the conductor. The first finger points in the direction of the magnetic field, and the second finger points in the direction of the current, and that is the conventional current. Another thing you have to know is that the size of the electromagnetic force is dependent on the size of the current and the strength of the magnetic field. It means that, well, what you should know is that the force is going to be stronger if the current in the conductor is higher, of a higher value, and the magnetic field, if stronger, will also produce a stronger force. So the size of the electromagnetic force is proportional to both the size of the current and the strength of the magnetic field. All right. So I think at this point we will do we will use a simulation of a simulation to show the electromagnetic force. So we're going to look at the diagram first, and this is showing how you can demonstrate the electromagnetic force. So we have a permanent magnet. So this is a horseshoe magnet being used here. Of course, between the poles, we'll have a uniform magnetic field. So we really need a strong horseshoe magnet. All right. We have a conductor AB. So this is maybe a thick piece of wire and connected in a circuit so that current flows through it. K here represents a switch, and the conventional current now is that taken from positive to negative. All right. So whenever you're using the Fleming's left-hand rule, Fleming's right-hand rule, the right-hand grip rule, all of these rules are based on conventional current, which is the direction of a positive, or the direction of positive charges if they were present. All right, so it's like imaginary current. All right, it's not the actual current, because the current is due to the electrons moving from negative to positive. But you cannot use that, or else you'll get it wrong. So you have to use a conventional current, which is from positive to negative. So when the switch here, K is the switch, when the switch is activated, current, we assume conventional current. So from positive going here up, around in the coil of wire here, then down, and from B to A, indicated by this pink arrow. So the current is coming out of the screen. And this is what you are to note. Magnetic field direction is vertically upwards, because we have the N pole here and the S pole here. So the magnetic field is going up. When the switch is closed, conventional current direction is from behind the screen. So from B to A, the electromagnetic force therefore acts to the left, causing the wire to swing from right to left. So the wire will swing to the left, all right, like that. All right, so we, okay, when I have the simulation here. So Miss Rose, you want to explain this one?
All right, so basically just as what was being discussed earlier, notice that we have a horseshoe magnet here set up, and we have our connections. So we'll have current flowing. Now, as is, this symbol is used when the current is going in, out of, sorry, or coming out of the screen or out of the paper. So if we use Fleming's left-hand rule here, and remember that the field lines for the magnet would be going from north to south. We're just gonna put in a few of these. So remember that your thumb would give the motion of the conductor. Your middle finger would point upwards or towards you, and your forefinger would point downward to show the direction of the magnetic field. Now, what happens now is that if we actually have a switch closed, then let's say that in this way, notice that the force, let's see if we can replay that. The force is from left to right, all right? If we were to switch the polarity of the magnet, then the force would be in the opposite direction, right?
Miss Rose,
All right. Yeah.
what you are to do is to move the wire. So switch the polarity so that we have the same polarity as in the diagram with the N at the bottom. So the magnetic field is going upwards. So if you move the wire, the force, the electromagnetic force will cause it to go back to the left. So just move the wire to the right and release it.
Okay.
Right? So it is showing that if the wire is inside the magnetic field, when the current is flowing through it, the electromagnetic force will cause it to go to the right, to the left, sorry. All right. So that's it. All right, so I'm gonna move on from here. All right, so this is the shape of the resultant magnetic field that creates the electromagnetic force. And notice it's similar to the field that you saw in the diagram, where it is as if the wire, it seems as if the field lines were being compressed towards each other and then released, right? So the magnetic field of the produced by the current in the wire will interact with the magnetic field from the magnet, causing on the right side the field to be strongest or stronger than on the left side. And where you have a differential in the field strength, a force will be exerted from the stronger area to the weaker area. All right. So that's how the electromagnetic force is created, by the interaction of the magnetic field from the current and the magnetic field from the magnet. All right, so we have a question which pertains to electromagnetism, well, electromagnetic force. And Miss Rose.
All right. So the figure shows the field that exists in the pole is strong magnet, right? Realize that we have our field is extending north, south. Next thing that we are asked to do is to determine the magnetic field that would be shown when there is a current carrying conductor and the current is directed into the plane of the paper, or in this case, it would be into the screen. Now we use a circle with an X to denote this, to show that the current is directed into the screen or into the plane of the paper. Now, to determine the magnetic field due to a current carrying conductor, we can utilize what is known as the right-hand grip rule, where your thumb basically is pointing in the direction of the current. So you would point your thumb away from you and into or towards the screen. Then your fingers would curl in the direction of the magnetic field. So basically your fingers would curl in a clockwise direction while the current is going into the screen. Okay. Now, the resulting magnetic field when the current carrying conductor in the previous question is placed between the poles of the magnet as shown in the figure. All right, so here we have a permanent magnet and we have the magnetic field lines. We know that they would extend from north to south. However, the current carrying conductor is now interacting with that magnetic field. So you're gonna have basically two magnetic fields interacting with each other as was described earlier, right? So what will happen is that as the current flows through the conductor and the magnetic field is clockwise, basically when you look at the top of the magnetic field, the field lines would be in the same direction. So you would have a stronger field there, or the field would be reinforced, whereas at the bottom, the magnetic field from the conductor and the magnetic field from the bar magnet, they would basically be in opposite directions. So they would cancel each other out. So there would be the resultant field of having higher or a stronger field at the top and a very weak one at the bottom. So you would end up with the conductor being pushed downwards in the magnetic field. All right, so we would draw our diagram to reflect this information. All right, so at the top, realize both of the field lines are in the same direction, so they reinforce each other. Whereas at the bottom, the fields would cancel each other out, so the strength is minimized there. Right? They cancel each other out there, so you have a weaker field there. And because the field is stronger at the top, it is going to force the conductor in the downward direction or in the opposite direction. So I think that's it for that question. So we're going to be moving on to our final topic, which is motors, and motors is directly related to the concept of electromagnetic force.
All right, so motors. The motor is based on the electromagnetic force. All right, so to understand the operation of the motor, you need to understand how the electromagnetic force comes into being, and that was explained earlier. Now, the motor is a machine that converts electrical energy into mechanical energy. specifically kinetic energy in the form of rotation. Now, motors are common devices because they can be found in appliances such as blenders, fans, washing machines, electric mixers, and DVD players. Even a computer hard drive will have a motor. Some computer hard drives. All right, what you should be able to do, explain the action of a DC motor, draw a diagram of a simple DC motor. Next, we have the simple diagram of a DC motor. We have a magnet, permanent magnet here, and placed between the magnet is a coil of wire, usually a rectangular coil for the simple diagram. And the free ends of the wire are connected to a device called a split ring commutator, which looks exactly like a ring cutting tool. So you get two C-shaped halves and touching each half of the split ring is a brush. All right, so very slightly touching it is a brush, and then the brushes connect to the electricity source. All right, so basically this is very simple to reproduce on an exam if you're asked to draw. All right, they can ask you to draw, but you know, you could just draw this simple diagram. All right, the principle of its operation. When current is applied to the coil, so when the current is on, so we're using conventional current again, current will flow to the brushes. The brushes pass the current to the split ring commutator, which then passes it to the coil. All right. All right, so the direction of the current flowing in the coil's left and right parts are opposite. Right, so if we're using conventional current in the left side of the coil, the current is going into the screen, while on the right side, it is coming out of the screen. So therefore, what that causes is the direction of the force which the coil receives is reversed, all right? And the coil rotates. So we'll have, for example, an upward force on the left side of the coil and a downward force on the right side. And those two forces cause the coil to rotate. All right. And I'm going to use a simulation just to do some further explanations. So again, we look at the simulation. Can we get it full screen? All right, so we can illustrate the magnetic field. We can look at the current. So on the left side, the current is going into the screen, while on the right side, it is coming out of the screen. So therefore, if we apply Fleming's left-hand rule, we'll find out that the force on the left side is going down, and the force on the right side is going up. So when we run the simulation, the coil should spin anti-clockwise. All right. Now, if we stop the simulation when the coil is vertical, I don't know if Ms. Rose can try to stop it when it's in vertical position. Okay. All right, notice that we do not see any current and we do not see any force. When the coil is in the vertical position, the brushes are no longer touching the split ring. The spaces between the split ring are now aligned with the brushes. So no current flows at that particular time. So there is no force on the conductor, on the coil. However, the coil does not stop, it continues to rotate. What causes the coil to rotate, or what causes it to continue to rotate? Now, to understand this rotation, we try to remember Newton's first law. All right, Newton's first law, which says that a body in motion will stay in motion. So if you remember that part of the law, a body at rest will stay at rest or continue to stay at rest. A body in motion will continue in motion unless acted upon by a resultant force. So what we see now is that the resultant force causes the coil to rotate. So the resultant force is the electromagnetic force, which initiated this rotation of the coil. However, the electromagnetic force stopped being exerted when the coil is in the vertical position. But because the coil was set in motion, it continues to rotate and not stop in the vertical position. This is similar to when riding a bicycle. When you pedal the bicycle, you set it in motion, but stop pedaling doesn't mean that the bicycle is going to stop immediately, right? So this is the same thing that happened with the coil. The coil was set in motion, so because it has that inertia, what we call inertia, it will continue to rotate even when the force is off. All right. So once the force set it in motion, it will not just stop because the force ceases to exist. So it will continue to rotate until it reaches the horizontal position again. And you can run the simulation again. All right. So it continues to rotate into the horizontal position. The force starts to act again. And so the coil continues to rotate because of its inertia. And the fact that each time the coil rotates, the split ring also changes position so that the force on a particular side of the coil reverses each time. All right. So this stop, Ms. Rose. If run it again a bit. Stop. Okay, so this split ring will go over this side. So this side of the coil, the left side of the coil will now be on the right. Current direction changes. And so the right side of the coil now start to go up. All right. And the left side, what I mean is that the side that was once going down will be on the opposite part of the setup. So it will now be over here, experiencing an upward force. So it was going down at first, but when it rotates and go over this side, it is now going to go up. So those that will cause the coil to continue to rotate because of the change, the reversal of the polarity each time with the split ring. All right. All right. So we can go back to the regular slides.
All right, so we're going to be looking at a work question. This is from the recent paper 2018 and question 6, part B. Now the figure shows the end view of a simple DC motor, and notice that we have different labelings. We have the north and south pole. We also have a section labeled A, we have B, C, and D, and we also have a portion called X, and we have our circuit setup. The first part asks for us to name the part labeled X, which is right here. You can see that this is a split ring commutator. Mhm. And it is responsible for ensuring that the the shaft keeps turning in the right direction each time as the current reverses, as the force reverses. Now, the same diagram, you're asked to explain what happens when the switch is closed, and we need to include the direction of the current, the forces acting, any rules applied, the direction of rotation, and how continuous rotation is achieved. So basically for 9 marks, we need to discuss or explain in detail everything that happens in order to cause the motor to keep moving how it ought to. All right. So of course, remember, we need to make sure that we mention the different parts. So once the switch is closed and current starts to flow, it encounters the brushes first, and then the brushes are slightly touching the commutator. So the current flows to the brushes, then to the commutator, and then through the coil. Now, based on conventional current always flows from the positive to the negative terminals of the battery. So on the right side of the coil, let's see if we can go back a little. On the right side of the coil, if we apply Fleming's left-hand rule, basically we could say that the current will be flowing into the screen. All right, so if we apply Fleming's left-hand rule, so the switch is closed, so we have current flowing through here and here. So current will be flowing into the screen. So if we apply Fleming's left-hand rule, notice that the force will be downwards, and on the left side, it would be upwards. Right? So on the right side, the force will be downwards, but on the left side, the force will be upwards. Now these forces will act together, so you will have the coil rotating in a clockwise direction, and eventually it's going to reach a point where the setup becomes vertical, or the shaft is vertical. And as was mentioned earlier, at this point, the brushes are no longer in contact with the commutator, so no current flows in the coil. However, because of inertia, all right, the coil is going to continue to rotate clockwise and achieve its horizontal position again, so that once again the brushes will contact the commutator, and now the brushes will touch the commutator on the opposite side. So the current direction is now going to reverse, and the coil will continue to rotate in the clockwise direction. So this process is going to repeat itself over and over. So once it reaches the vertical position, inertia will force the shaft to continue its clockwise rotation, and the brushes will continue to contact the commutator. All right. So it's a very long explanation. It's all of 9 marks. So you have to ensure that you mention the different forces acting, the direction of the current, mention Fleming's left-hand rule, as well as the direction of the rotation, and ensure that you mention how the commutator and the brushes go, as well as Newton's first law of motion, which speaks to inertia, how all of these work together in order for you to explain how the continuous rotation of the coil is achieved. Okay. So I'll hand over to Mr. Campbell once again, so we can just finish up and we'll take any questions you may have.
All right, so actually this is the end of the presentation. We do not have any more questions at this point. Please remember, you can subscribe to our channel. That's Menelik on JM. You can like our Facebook page and Instagram page. All right, and feel free to share. If there are any questions, we can take them now. All right, where is the recording going to be? We are waiting to finish the session before we decide what to do with the recording, because we don't want it to seem I'm not sure what to say, but because this is a paid for session, I don't want to put it out so that, you know, you guys have paid, you are privileged to it, right? So we prefer to have the sessions finished first before we release it.